We have a bunch of technologies that we call thought flows, and these are all designed to be really streamlined for the user to do. So some of the major ones, we have attribute generation. We are able to generate over hundreds of attributes in Paradise using just a base stack, full stack. Now, if you bring in any of your angle stacks, multiply that by how many angle stacks you have. So you can generate attributes on all your stuff, right? Our bread and butter is our self-organizing map or our stratigraphic analysis, and most of our technology stems off of our stratigraphic analysis. We have all these now. One of the big pushes from customers is, how do I tie this all with the well? So we've worked heavily on our well log visualization and well log cross plots. We have a new tool called the well analysis dashboard, which allows a user to completely interact and get a comprehensive understanding of their wells, the relationships between their seismic data and their well log properties. We now tie this together with our newest release, came out in August 2024, called Lithophase Prediction, which is what you see here on all the marketing stuff, is showing you how you can use both wells and our stratigraphic analysis to predict lithophases in your subsurface. Furthermore, we have a few different supervised machine learning techniques. Our biggest one is automatic fault detection. It's really, really good. So your user, you've never looked at your data before, you don't want to sit there and manually interpret faults for 2 weeks. You come in, you run automatic fault detection. It gives you a volume, you put it into Petrel, run surface extraction, boom, you got all these fault services, and it beats the snot out of Petrel and tracking. We also have seismic facies classification. So if you're digitizing, you want to predict this, you want to make a 3D rendering of your salt, draw a polygon around your salt, 1 or 2 lines, click go, boom, you got a 3D salt, right? So there's a lot of really powerful things in Paradise that we have. So our last one is from all of our outputs. All of these outputs, we have the ability to make machine learning driven geobodies. So whether it be a lithofacies volume, you can make a lithofacies geobody. You can make stratigraphic analysis geobodies just off basic other seismic features. You can make fault geobodies if you wanted to merge faults together. You make a facies geobody. So all of these, we have the ability to create machine learning based geobodies, and you can actually apply any of the well log property volumetrics to any of our geobody outputs. So say you identify a geobody of the reservoir, you know the water saturation, you know the growth pay, you know the porosity. Do that, you can get a volumetric calculation of your reservoir. All right, so here's some of the main idea of all of our thought flows. We have our attribute generation I briefly mentioned. We're actually we're the sole proprietor of the distribution of the ASPE attribute generation. So this is a research group out of the University of Oklahoma, ASPE attributes, and they have a very, very vast library of attributes that you're actually able to generate. So we're the only company that's allowed to actually license and sell the ASPE software, and we wrap it. One of the big issues with ASPE, because it's a research group out of Oklahoma, a bunch of students, the interface is, to be said, needs improvement, and so we're actually able to generate all their backend code in a nice, easy to use interface. I'll show you guys some examples of that stuff. Right? We have attribute generation. I mentioned we can generate hundreds of attributes. Color blending. I know a lot of products on the market have RGB color blending. So we have the ability to. This is what I would call a 3-dimensional cross plot. Right? One's being your red band, your green band, and your blue band. So this is what you can do: 3D RGB color blending. Attribute selection. So we have a few different techniques for attribute selection. What attributes do I use? Obviously, one of the major ones is principal component analysis, which a lot of people use. And I now there's a new methodology coming out which chooses attributes based off the statistical relationship to your target wells. So this is we're really excited about that new technology. Stratigraphic analysis is our self-organizing map, trying to find clusters in high dimension space. And additionally, we have our 2D color map, which is a proprietary technique that we have that allows you to isolate things in our 3D viewers. I'll show you a live demo of why our 2D color map is so powerful. You can highlight things, and it really, really highlights geologic features. I've mentioned before, we've done a lot of work moving to the well, so we're working a lot on well log visualization, well log cross plots, how do we do a comprehensive analysis of all our well data, how does that relate to our seismic attributes. Our latest release is our lithofacies prediction module. It was released in August 2024, and I'll be showing you all a lot of results of that. Geobodies, all of these outputs can make machine learning geobodies, and as we mentioned with our stratigraphic analysis, that all these machine learning geobodies, they're technically formed from a multi-attribute analysis. So that's what makes us different than a lot of the other companies. You can do an RGB color blending which is technically three attributes, right? But with our geobodies and our self-organizing map, you can use up to 50 attributes to make these machine learning driven geobodies. So it gives us a really, really competitive advantage and allows you to see detail that normally the eye couldn't see. And I'll show you some examples of that. Seismic facies classification. We have the ability to do CNN-based seismic facies classification. So if you want to just digitize a salt body, for example, you digitize it, train a model, then apply that model to the rest of your data set. Fault detection, you'll see some results of our automatic fault detection. It's really easy. Paradise ships with fully pre-trained 3D models, so the user doesn't actually have to train any AI. It's just, here you go, we have it built for you. We have 3 models, a high-angle fault model, a mixed-angle fault model, and we're working into these.
Low-angle fault model.
Yeah, we're working on low-angle thrust faults and strike slips. So if you look at it, like say a strike slip model and an inline and cross line, it's going to be very difficult to see, right? You need to have it look from the top down. So a lot of our competitors use 2D faults. We're just looking along a section. Now, we train pure 3D fault models, which part of the process of training is we take these mini subcubes and we rotate them in 3D. So you can look at this mini subcube in all these dimensions, right? Now, being able to do that, and when you actually go to apply our fault model, it's rotating the subcube in all these dimensions. So you're actually able to capture some of those offsets that are normally harder to find if you're just looking at a pure inline or cross-line display. So that's one of the power of a 3D pre-trained model versus all these traditional 2D models, which just it's essentially looking at a picture and telling me if it's a fault, right? It's the equivalent of, is this a picture of a cat or not a cat, right? Here though, it's looking at not just a picture of a cat, it's a 3D image of a cat rotating all these ways. Okay, this is actually a cat. That's where the power of a 3D model is versus just a 2D image. Yeah, so we ship with 3D pictures, a 3D predictor.
Till which angle you can really predict it in 3D.
Yep. So we're working on our library of pre-trained models, right? So we've had a lot of requests of low-angle thrust faults, strike slip faults, all these. It's very easy to do. Right now we only ship 3 different, primarily normal fault predictors. But to be fair, it mainly looks for the main driver of it is looking for seismic discontinuities, right? So if there's any type of offset, it's going to do a pretty good job of predicting, right? And sometimes there's some false positives and there's some cleanup tools that are user-driven to help you clean up and get a better prediction. So here are the 2 main basic approaches to machine learning. I got 2 highlighted here. One is unsupervised machine learning, which is what we refer to as a clustering algorithm, and the other one is supervised machine learning. So what unsupervised machine learning is, it's going to look at the inputs. You see here I have 5 pictures, right? And it's going to look for similarities between those inputs. So you see here, naturally it's going to find that, hey, these all look kind of similar. We're going to put them in group A. There's nothing look like this and nothing look like that. So they're going to be put in different groups. This is the basis of our self-organizing map. So you can imagine each of these is a seismic sample and it has details of it, which includes all of the different attribute properties for that single seismic sample, that single location in XYZ, right? So you have the sweetness for that sample, the amplitude for that sample, essentially 150, 200 different attribute properties for that single XYZ location, right? It's going to find attributes with similar seismic properties and then group them together. And so this is where, when I say a traditional, say, 2D attribute cross plot, you might be able to do this in 2D and you could probably manually interpret it. You can do 3 dimensions, which is RGB blending, and you might be able to interpret it. But how do you do that with 8 dimensions, 10 dimensions of data, right? The human eye can't see it. And so that's where you use a machine to try to find patterns in high dimension space that otherwise the human eye would not be able to see. Now, the second one is a classification algorithm, also known as supervised machine learning. And the key to this one is it's labeled. You see here how it says there's a label there, duck, duck, and then these 2 are labeled not duck, right? What you do is you take these labels, you take the inputs, and you use this to make a predictive supervised machine learning model. You then give it some external data, and you want it to tell you, is this a duck or not a duck, right? This is the best way to explain how faults work or how facies work. Right, so you determine, all right, I'm going to give you this set of seismic data. This area is a salt, right? Now give me this other line. Tell me, is this a salt or not a salt, right? Or is this a facies? Is this a fault? So this is the primary basis of how supervised machine learning works. And this is where, however you define those labels, if you do it in 2D versus 3D, it's going to give you different predictive results. Now and then another approach is what we call semi-supervised machine learning. It's a combination of the two. So for example, you can use your outputs of your supervised machine learning algorithm as inputs into your clustering. So this is a combination of using both unsupervised machine learning and supervised machine learning in a single workflow. And you'll see here, it's really powerful, and it actually helps you compartmentalize your reservoir, and I'll show you guys some examples of that. Reinforcement learning too, I'm not going to talk about. One of them is called reinforcement learning. It's a machine learning algorithm that optimizes for a positive result. So if you're building, say, a chess bot, right, or something that's going to be a video game or something like that you're building an AI for a video game, the reward is that it wins, and so it's going to keep changing and tweaking its coefficients for its matrix until it converges to a solution that's going to win, right? So you keep rewarding it, so it's called reinforcement learning. And then self-supervised learning, which is what a lot of the generative AI and LLMs are. The way they work is you train it using, say, a document, and you don't need to put labels on it because it's self-supervised. Like even this, it'll know, say I'm trying to train on the word ML, it'll know because it has the word tokenized model, that improves. It'll use this all in its own, it's already self-labeled because it knows this is here, then following it are those three words. And if you have the word involves previously are those three words. So this is what you call self-supervising. Because of the nature of the data itself, it self-supervises itself as it trains. So it knows, because it knows the word previously in the sequence that comes before, it can help you predict the word that comes in the sequence after. All right, so this is how generative AI and LLMs work. It's something called self-supervised. So here's an example of Paradise's self-organizing map. It's unsupervised machine learning. All right, so here's an example of 6 seismic attributes. I have my envelope, my sweetness, my similarity total energy, amplitude, Hilbert, instantaneous phase. Now if you were to do a cross-plot on a few of these, you might be able to pull out some patterns, right? But what we do is we're going to plot all of these in high dimension space, and we're going to make what's called a self-organizing map. So here is what we call an 8x8 self-organizing map. So there's 64 natural clusters, and in each of those natural clusters, it means the attributes had very similar properties, right? So if I were to look at cluster 4 or cluster 5, it means that those attributes that make up cluster 4, those seismic samples, are highly related to each other because they have similar seismic properties across all the attributes used in the analysis. And so you'll see here that doing this, you're actually going to be able to pull out some geology. So here's a good example of this. We have seismic attribute 1 versus seismic attribute 2. And if I was, say, draw me 4 natural clusters on this, or try to group this in data, you can probably go cluster here, cluster here, cluster here, or we'll have machine learning. All right, let's find this 4 natural clusters. So I take this, and it's going to give each of these a different label. So I have my neuron 1, neuron 2, neuron 3, neuron 4. Right, and each of these clusters are called neurons or nodes. So that's what when you refer to neuron, it's referring to a cluster in attribute space. So here's just another quick example. This represents a single seismic trace. So here's the amplitude along that trace, here's the Hilbert, the instantaneous frequency. And you can plot each of these in, say, a 3-dimensional cross plot. And you might be able to interpret it, right? It might be able to give you a polygon lasso tool, and you might be like, I'm going to try to group that, I'm going to try to group that, I'm going to try to group that, I'm going to try to group that. But imagine plotting all 8 of these together. That's 8-dimensional space. Right? I don't think anybody's going to be able to try to plot and group seismic data on 8-dimensional space. So this is where you use a machine learning algorithm such as self-organizing maps to try to group seismic data in 8-dimensional space. You'll hear me refer to this a lot as attribute space. It's easy to visualize in 2 dimensions, but 3 dimensions, 4 dimensions, 8 dimensions, 25 dimensions. This is why we have a self-organizing map in our SOM, because it's going to help you analyze data in high dimensions. And why it's important is these relationships in attribute space can directly correlate to geology. Right? You can see this. You can see a channel right here clearly going through. And yeah, you could probably manually interpret it. It'd take a long time. But I made a self-organizing map, and what do you know? My channel pops out clearly in attribute space by doing a high dimensional analysis. So here's an example. We're going to go into lithophase prediction. We're going to take the technology I just showed you and use the well data to assign different meaning to each of those individual neurons. So we start off with our seismic attributes, and from there we generate machine learning clusters, which is our self-organizing map. Now we're going to have a completely separate data source, our well logs. You start with your petrophysics, and we're going to use that to generate lithofaces along our wellbore. Now we'll add a caveat, it doesn't have to be lithofaces, it can be net pay or net reservoir. We also did a project for a client, and he just wanted to purely he made a banded porosity log. So this is my high porosity, low porosity, medium porosity zone, right? So it doesn't have to particularly be lithofaces, but it mainly has to just be categorical descriptors of how you want to break apart your wells. Here's an example of the test area I'm going to show you. It's the Niobrara Shale, part of the DJ Basin, kind of here in northeastern Colorado, southeastern Wyoming. See this basin? And the key formations we're going to focus on is the Niobrara Formation. So the Niobrara Formation is made up of all this. Niobrara A, B, C are chalks, so porous carbonates, right? In between them, it's intermingled with these marls and shales and dolostones. And the key thing is that it sits on top of this Fort Hays limestone, which is shown in the wells as being a much tighter carbonate. So you have a bunch of porous carbonates sitting on top of a tight carbonate with intermingled shales and dolostones. So here's an example of my well. So you can see here I have my volume of calcite curve, DFV calcite. Right here you can see there's a high calcite band. That's my A bench of the Niobrara. This B bench, which is the main producer of the field, see it going across, this is my B bench of the Niobrara. It has a high volume of calcite and a high porosity. The second curve is my high porosity. My porosity log curve. I have the C bench of the Niobrara. You can see it here. You have a high volume of calcite, high porosity, and you can see that there's some intermingled shale in there. And then finally, the Fort Hays limestone, which you can see on the porosity curve, it's much tighter here than it was in all my chalks. So it's defined as being high volume of calcite, but low porosity. And in between these, you have all these different dolostones and shales. So our expected sequence for this study area, we have our A bench chalk, followed by some dolostones with some shale and some dolostone. You can see that on all these sections. The B bench chalk, which is the main producer of the field, with some dolostones and shales kind of in between there. The C bench chalk, you can see here with some dolostones before finally you get to this brighter, high porosity Fort Hays limestone, followed by some shales and shocks beneath it, and finally another series of dolostone that at least show up on our wells. Did this make sense to everybody, the expected sequence? Right. So this is our amplitude. This is what we're dealing with, right? All of that information I showed you lives here, right? So we're going to try to pull out all of these shales, all these chalks, just within a few peaks and troughs. In doing that,
What is the thickness we are talking about here?
I think it's in time. It's not very thick. It's only a couple hundred feet, or maybe like 300 feet. I'll have to get you the actual thickness, but it's some of this stuff we're imaging is to a seismic sample. So if you were to zoom in, some of these layers, some of these clusters are literally a single seismic sample thick. You kind of see me trace along this. I'll show you just this bright blue one because it shows my point. Some of these are literally, these clusters are a seismic sample thick. So we're able to process seismic data at seismic resolution, right? We're going beyond the wavelength, right? We're going beyond the wavelength because we're making this high dimensional analysis that cross plots this stuff in n dimensions, right? Depending on what you want to do. This particular SOM was done using 8 different attributes, right? So 8 dimensional analysis. Now, our goal is, how do we take this self-organizing map, how do I turn it to lithofaces? Because that's actually what we're interested in, right? This is interesting, this is fascinating. It showed you that this is how my data clustered in n-dimensional space. Right? This is the natural clusters. I didn't do anything here. I plotted it and I said, show me the natural clusters of my data. Now, how do I take those natural clusters, how do I convert it into lithofaces that are going to be interpretable for me as a geoscientist? And that's where our lithofaces prediction tool comes in. So what I've done is I've extracted my self-organizing map and the seismic trace at the well. Right, so you can see here, here's the Buxman well. You can see here's my self-organizing map that I just showed you. I extracted it at the well. Here's the seismic trace. So this is what we're dealing with. It's only a few peaks and troughs for each of these wells. And to answer your question, it starts at 6,800 feet and it goes to about 7,200 feet. So this is about 400 feet a section. So what is that, about 115 meters of section, approximately? All right, so we're dealing with about 100 meters of section, right? A little longer than a football pitch, right? So this is what we're dealing with and trying to interpret, right? So in here, what we're going to do is we're going to count. It's a frequentist approach. We're going to count how often, when a lithofacies shows up, how often does it intersect of neuron of interest. So I can even go down here. What neurons intersect my limestone facies? What neurons intersect my chalk facies? What neurons intersect my shale facies? And we're going to make a comprehensive analytical dashboard using this information. And we're going to use it to map our SOM neurons to our lithofacies of interest. So we're going to use this and we're going to map it. So here's our lithofacies prediction dashboard. So a good example here is neuron 44. Across all the wells in my study area, neuron 44 showed up 80 times, all right, along that section. And of those 80 times it showed up, 78 times it was limestone, and only 2 times it was chalk, which is pretty good considering that there's definitely some porous limestone, some porous carbonate, and you can see here that there's some intermingled tight carbonate and porous carbonate. We're dealing with well resolution. So having a 100% fit is never going to be realistic because well resolution is seismic resolution. But what this tells us is that's a pretty darn good indicator of my four-phase limestone, right? And all these other ones are good indicators of my limestone.
This display is on a horizontal axis. They're all the neurons that were generated from 1 to, how many are there?
64.
And then it shows you what it found in where that neuron, how many times it showed up in those wells. So the vertical axis is count.
We have all these different fit metrics too for how well your different self-organizing map matched to your lithofacies log, the biggest one being Kramer's V. If you have above a 0.45 Kramer's V, Kramer's V is a measure of statistical fit between two categorical variables. And so if you have above a 0.45 Kramer's V, it's a very, very good statistical fit.
So in the plot, it's kind of a multi-dimensional crossplot.
Yeah.
Okay.
Now, so what we've done is, so now we have our self-organizing map, and we've calculated we're going to use this to calculate the probability of each neuron. So you saw here that we're focusing on it. And what this is doing is, all right, limestone showed up 78 out of 80 times, so I'm not going to do quick head math, but that's like a 95% probability that neuron 44 is a limestone, based off my well data, right? So you see here the neuron next to it, this one's a little weaker, so we can tell it's a carbonate, right? Because it has either chalk or limestone in it, but it's not a high probability. We don't know whether it's porous or tight based off how often it showed up along the wells. So you see here in neuron 43, it's a low probability limestone. So it won. There were more limestones than there were chalks. So you can see how we shaded it kind of light blue, right? That means it's lower probability. So if it's a darker shade, it's a higher probability lithofacies, at least based off our well data. And if it's a lighter shade of that color, it's a lower probability.
And the white neuron, they are not classified? Or what?
They didn't exist along our wellbore.
Okay.
That doesn't mean that they're bad neurons. Like, for example, if you add faults to this analysis, you expect those fault neurons to not show up because you didn't hit it with your wellbore, which is a good thing, right? And we all know that geology on this mountain might not match geology on this mountain. And you may not want your well. It's not necessarily a bad thing that you're missing neurons. It means that your wells didn't sample that geology, right? So we have no statistical measure of how the self-organizing map mapped to the neurons that your wells never hit, right? So it's just something to keep in mind as you run this. You might not actually hit all of the different clusters along your wellbore. This is just a measure of how it is along your wellbore. Now we're going to take this, we have our probability map, and now we know how we can map our neurons to specific lithofacies, right? So I'll show you what it looks like. It starts out like this. Now I'm going to take this, I'm going to map it to lithofacies, and now I have an actual section that shows my lithofacies using this clustering algorithm. And here's my expected sequence. I have my A bench, I have dolostones and shales in between. You can see this B bench going very well across with a really high probability. This is the main producer of the field. We have below the B bench, we have some shales and chalks here. So now we have that shale bed between the B bench. We have the C bench. Below the C bench, we have some dolostones. Finally, we have this Fort Hayes limestone with some shales and porous chalks underneath. You can kind of see that going along here. And finally, another dolostone layer. So we're able to.
So, can I?
So I'm going to take this. I just figured I'll isolate these shales right here. I'll take this shale bed, and I wanted to make you can make a 3D shale geobody with that. So now I have a 3D representation of that shale layer, right? Which in some places is only a seismic sample thick, right? So this is where this is a really, really powerful technology in making 3D geobodies. If I use my reservoir, I can apply all the different volumetrics and get an actual calculation. All right, so here's an additional slide, additional lithophase prediction study that we did in West Desert, Egypt. You can see here, this one kind of jumps out at you. We have two different facies. So I have my pay sand and my wet sand. This is a series that has carbonates and sand in it. And clearly you see this neuron is my wet sand. That neuron is my pay sand. This self-organizing map did a really good job locking onto those particular facies. You see here, this is what it looked like along my well. I have my pay sand here, and this is one of the good big producers of the field. And then here's some other areas of pay that could be of interest with similar seismic signatures, or I'll say not just seismic, but attribute signatures, right? Because this is an n-dimensional analysis. And from there, I can generate 3D probability cubes of the reservoir, right? So you can see the pay sand, you can see the wet sand, and here's a full 3D cube of my reservoir, which is using my self-organizing map. And we recently just came out with probability cubes. This is a 0 to 1 probability cube. I used an opacity filter to kind of hide the samples that were low probability.
Probability calculated based on weighting on attribute, or how
It's based off the self-organizing map and how often the SOM neuron matched that particular lithofacies. So it's all driven from that lithofacies prediction dashboard. Right, but it does a really, really good job of mapping our reservoir with the pay sand and the wet sand underneath, and you can see this all over. And what's great is this was the dry hole. This one here is the dry hole. They didn't hit any reservoir, right? You can see that there was some there, but it wasn't quite spot on. And using our analysis, our self-organizing map confirmed that. This was a blind well, and it confirmed that they didn't expect to see reservoir there. And what do you know? It was a blind well. So it does a really good job of confirming what we expected to see using the self-organizing map. If you want to know more about this, this is a presentation done by Robin Demise. So University of Texas, the Bureau of Economic Geology. He's a senior geophysical advisor. We gave him the software with limited training. All he did was watch a webinar of me and my coworker Alvaro for about an hour. We gave him a version of the software. And he had 3 PhD students doing an inversion project. And his 3 PhDs took 3 weeks to generate that result. We got a nice email from Robin saying, you guys got to see this. He told us that he locked himself in his office with 3 pots of coffee, and within 12 hours, never trained formally on the software, was able to generate that. So this was his result in 12 hours. This was a result in 3 weeks with 3 PhD students doing a traditional seismic inversion. So this was one of the best real cases that we've ever shown, where someone took the software, sight unseen, used it, and was able to generate a result in a fraction of the time of seismic conversion using the self-organizing map process.
Yeah, with
Snapshot of our interface. It's really easy to run jobs. So my job as a product manager is to build software that not just is comprehensive, but is easy to run. Because I am a self-taught Petrel user. Didn't go through any formal training. And doing that off the rip by yourself is not the easiest to teach yourself how to use Petrel and to get the most out of all their workflows. So when you use SOM, we're known for what we call our blue button thought flows. It's really easy. So I'd click on our self-organizing map. I want to create or edit an old one. Choose my domain. It'll automatically filter for your survey based if it's a time or depth survey or a different zone. You choose your attributes. You choose your data delimiter where you want to run it. Filter some parameters and click go. So it's the easiest thing to run Paradise. So when someone's here, if I were to give you an example of the software, and y'all are more than welcome to play around with it, it's very easy to get up and running and actually run our thought flows. Same with PCA, and I'll show you an example of some of our fault detection results here in a second. So now we're going to take another step back. So I showed you our self-organizing map, which is our unsupervised machine learning. Now I'm going to show you our supervised machine learning, which is our fault and our facies. All right, so it's a two-step process, and you use data labels. So because your data is labeled, your engine, I'm going to refer to a predictive model as an engine. All right, this is my predictive engine. Because your engine is as good as your labels, if you have misinterpreted data, it's going to have poor results. If I were to give a seismic section to 25 geoscientists, and I say, all right, draw me faults, there'll be some similarities, but you're going to have 25 different answers. Right? So we ship with pre-trained models because it's going to eliminate bias. So we know it's voxel perfect accuracy. We made a synthetic build, and we put a fault there by design, added a bunch of Gaussian noise, and here's my fault model. Right? So you see, here's my input data, here's my data label, here's my input data, here's my data label. We do this with thousands of synthetic cubes with different various offsets and curvatures of the faults to generate our synthetic fault models. We then train an engine, and now once you have an engine, you can apply it to any result. Right? So just a quick example, none of this was manually interpreted, just click go, and here's some faults. Right? This is just saved. This is what I would call, there's two camps of machine learning, either faster results or better results. This is what I would call in the camp of way faster. It's going to just get rid of your job of having to do tedious manual fault interpretation. So we have something called the advanced fault workflow. So as you talked about data conditioning, right? So what we do is it's automatically going to precondition your data. So it's like when you do like a gather cleanup before you do radon, right, to do demultiple, right? You want to condition your gathers because you don't actually care about, you're trying to smack your gathers because you're trying to iterate on the velocity, right? So you don't really care about preserving primary versus noise, right? You want to just condition your gathers, right? So we do a very heavy preconditioning of your seismic data. We're going to run our CNN, our fault probability cube. We also have a series of post-CNN or post-machine learning fault cleanup, which is called our enhanced fault volume. You export that to Petrel or Kingdom, whatever your interpretation package is, and then click go and you got fault services. So it's a really, really quick way to generate fault services that are machine learning driven and way better than ant tracking has ever given us. Right? So what it does, it's going to eliminate bias. It's going to make it so you don't have to actually do manual fault picking. It's going to eliminate uncertainty of which lines to actually digitize to train a model. So I want to train a model, I don't know what lines to do. This seismic doesn't look like that seismic, which doesn't look like this seismic. You have varying geology across your entire survey. And it produces consistent fault probability results rapidly. So it's quick. And then you can generate fault surfaces from that interpretation really easily. So that's what it's meant to speed up the general interpreter. And here's just an example of, here are the fault results for Petrel ant tracking, and here are our fault results, right? It's so much faster and smoother. And you just click go, and boom, you already got some faults. Here's an example of that semi-supervised machine learning technique I talked about. So in my self-organizing map, I use both stratigraphic attributes and fault attributes. So coming out of that fault CNN, you don't just have the fault probability cube, you have the fault azimuth cube and the fault dip cube. Right, so it shows you can use that to separate east from west dipping faults. You get different stratigraphic or structural regimes, or you have faulting in one direction and faulting in another direction at two different geologic time periods. Right, you can use this technique in your self-organizing map to, based off both the azimuth and dip of those faults, to have these cluster together with your stratigraphic attributes. So now you're going to have a comprehensive model, comprehensive self-organizing map that has both the stratigraphic attributes and the fault attributes. So if you were to put this self-organizing map into your lithofacies prediction that I showed you earlier, right? Some of these neurons are going to be your lithofacies, and you'd expect the fault neurons to not actually hit your well bore if you drilled your wells correctly, right? You don't want to drill your well, unless you're targeting a fault or targeting something, you don't want to drill your well straight through a fault, right? So that's an example of where you can use both of those together, and you would have a compartmentalized reservoir, right? So you know that neuron is going to hit that that fault, and that fault is classified already as a different neuron, just because it has a fault probability and the other doesn't. So this is something we just released in our release that just came out here in April, a few months ago. So we've a big outstanding request from users is, all right, I like the 3D stuff. I want to interpret my own though. Okay, so we gave it to you. You have the ability, if you want to, you can digitize some faults, use that to train a model, and then you can have your own 2D faults if you want to actually train it yourself. So actually this particular one I did, it took me about 3 minutes to digitize 2 to 3 lines, just click, 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 go, train, done. I now have a full 3D cube of my faults. And this is actually, and so why labels are important is this turns in, when you go to label, it turns into 1 is a fault and 0 is not a fault. Now what that's important to telling the model as it's predicting is it's not just telling it where the fault is, it's telling it where the fault isn't by having no pick there. Right? So that's one of the keys here. It's not just telling it where the fault is, but the fact that I didn't pick down here and I didn't pick down here is telling me precisely where the fault isn't, right? Or where you don't think there's a fault. So this all goes into the model weights and why you might want to have this type of approach. So it's really nice. I like it for isolating powerful, large regional faults. I don't want all those false positives. I know the clear as day, this is the fault, that's the fault, that click, 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 done. 10 lines over, click, 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 done. Do it 3 times, 4 times, takes me about 10 minutes, train, and here we go, I got a full fault model. It's really easy. Here's some additional case studies. One of them, I'll show you quickly, just this is, these 3 case studies are going to show you a comprehensive list of how we apply all the technology stacks in here in offshore India. We did a project in the last 6 months that used all this. So the first one, we're looking for hazard identification using both our amplitude and our fault detection. So the first thing we want to do is we want to identify faults in this shallow section, right? So we're looking for shallow hazards. We want to identify faults in this shallow section. So we ran our automatic fault detection, and this is what we got. We got some pretty good fault results. The user didn't have to come in here, didn't have to pick anything, right? So it's really, really easy. Just click go, and here are my faults, right? We then want to, from there, we want to identify these shallow hazard pockets, or these shallow hazard bright anomalies. So as we're drilling, we want to dodge shallow gas pockets, other faults, changes in attenuation. And we're looking for bright spots, right? So we're going to look for gas chimneys, pipes, pockmarks, channels, scarps, anything here on the seabed that we should dodge or in the shallow section that we should dodge as we're drilling. So we're going to use our self-organizing map now and our faults to kind of identify where are some hazardous areas that we want to drill. So we have our fault detection, and now we ran a self-organizing map that is looking for bright spots. So we ran the SOM, we ran a 5x5, so I wanted 25 natural clusters, and I'm going to look for bright zones. And after doing this, we identified these are the shallow anomalies that we want to avoid, particularly in this zone of interest down here. So we saw that after running this analysis, these are the faults, or these are the bright spots that we want to avoid after running my self-organizing map. Here are the key attributes that we ended up using. So here's a zoom in of that same section. You can see the faults here. Here's my self-organizing map. And this is where these natural data clusters are so powerful, because manually interpreting this by hand is going to be really difficult. But using our self-organizing map, all of these clusters have naturally the same seismic properties across all the attributes that I used in my analysis. Right? So I can overlay the faults here. I have my self-organizing map. And then these are the bright spot anomalies that we identified that we want to dodge as we go upon our drilling. And if you overlay it, here's an example of where they are on the seismic. So you can see here, these are the zones of interest that we want to dodge. And from those SOM neurons, we go into our geobody thought flow. You choose the SOM or the classification. Right, neuron 16 is the one I want to make geobodies of. That was the one that we highlighted as the shallow anomalies. And then you can click go, and then you can actually make shallow hazard geobodies. So here's what we identified. So here's an example of all the outputs together. You can see here these blue areas we identified as possible overpressure. So you have these blue neurons here, and underneath it is that thin gas reservoir. Right, so you can see one neuron we identified as a thin gas reservoir. We have a few neurons here. There's these blue neurons, which are our possible shallow hazards, our bright spot anomalies that we want to avoid. Now we're going to look at this exact same thing top down, and we've overlain it with a horizon of the seafloor, which has a high dip. So these are the canyons of the seafloor that we don't want to drill. So now you can see from the map view a very good idea of the possible hazards, that representative hazards in our zone of interest. So we have all the faults. We're looking down, so we have all the faults in our zone. You can see here the black ones are the faults. The purple is the dip of the seabed, so it's a horizon, a surface that represents very stippling parts of the seabed. These blue neurons are the shallow hazard zones that we want to try to avoid. And finally, you can see that red thin gas reservoir that we might want to target. Right? So this is how showing all these different machine learning technologies used together to make a comprehensive interpretation of our shallow hazards and of our subsurface. All right, so we're going to do another case study is lithophase prediction in offshore India. This is the east coast of the peninsula, and they only give us a single well to work with. So all this is done using a single well, and this was the well. So we're going to try to identify where's the reservoir here, and these were the different attributes we chose to use. So we use acceleration of phase, amplitude, attenuation, bandwidth, envelope second derivative, envelope slope, Hilbert, frequency, instantaneous frequency, relative acoustic impedance, sweetness, and thin bed. So these are the attributes that we decided to use in this analysis. So it was an 11 attribute self-organizing map. And just to show you how different these attributes are, this is an example of the 11 attributes that we used to run our self-organizing map. So here's the self-organizing map we ran. We ran a 10 by 10, so there's 100 different neurons, 100 different data clusters, and this took what they describe as a fraction of the time from a typical inversion-based result. We then ran our lithophase prediction, and we identified these neurons as our gas sand and that neuron as our wet sand. So it appears to be on par with what they expected from the inversion-based, from what our client said. So you can see here we went from the seismic I showed you originally to this lithophase prediction result, where this is my pay sand, these are my wet sands. Just to give you another example of how we do lithophase prediction, here's our discrete log. Neuron 23 showed up here, so this would have a 75% gas sand probability and a 25% shale probability, because here's a shale here, and here's 3 of these 4 samples were gas sand, so it makes 75% probability. Here's an example of the detail we're working with. So each of these seismic samples was about 5 meters of thickness, and we identified these different gas sands. So here's the actual lithophase log, and here's the self-organizing map based off winning neuron, and you can see which neurons matched up with each of our lithophase log, with the reds being the gas sand and the blues being the wet sand. Zoom in a little bit, you can see we have a pretty good matching. We're dealing with the seismic sample resolution. Here are those 2 different reservoirs between our Pleistocene sand. So we're actually able to pull out this very, very, very thin, small reservoir down to the sample thickness. This is a really clever display. So I have the amplitude, and you can see we kind of made it granular so you can see the seismic samples. You can see kind of how it's pixelated, right? So that's the resolution we're working with, right? So this is the seismic resolution. Now this is the self-organizing map, and you can see how we're able to break apart these neurons. That one's 2 samples thick, got 1 sample thick. And here's the lithophase prediction. So now we've identified which neurons that we think are our pay sands. You can see that it's here, right? So it's just only to a few seismic, samples thick from seismic resolution. And then it repeats. We have our amplitude, our self-organizing map, our lithophases, amplitude, sample, self-organizing map, lithophases. So we're able to pull this out. Here's our lithophase prediction result. This is the key neuron that we're going to focus on. Neuron 12 is our high probability one. The rest of them we don't have a good correlation, but we found that this one was a good example of our pay sand. And now we make gas sand geobodies. All right, so you see here we have all of our gas sand geobodies that we were able to pull out from those particular neurons, and now we can look at them in 3 dimensions. All right, so here are our gas sand geobodies. Neuron 11 wasn't penetrated by the well path, so we don't know exactly what it is, but we connected it manually. So you can go in here and you can manually connect, you can manually change neurons. So because we didn't intersect neuron 11, but after manual interpretation, the interpreter made the call that they think that this neuron is part of the reservoir. So they've combined it with the rest of the neurons to generate their gas hand geobodies. And now we have a much more continuous reservoir. But it just happened that neuron 11 wasn't penetrated from the well, so we didn't have any statistics on it. But this is where there's a little bit of nuance with being a good interpreter, right? And making the judgment call that I actually think that neuron is a part of the reservoir, and now we connect it, and we have a really nice comprehensive gas sand, or continual gas sand. Here's another example. We changed that neuron to gas sand. Now we've overlaid it with the lithophase prediction volume and the amplitude. You can see here that it's only a few samples thick. Right? It's only a few samples thick compared to the rest of the survey. Here's a bigger zoom out of the faults in addition to the gas sand geobodies. Now I'm going to move into the next stage of it. So we've done the first part, which is shallow hazard detection. Now the next part was our lithophase prediction to identify the reservoir. Now we're going to do a larger AI fault detection. So now this is us running the faults. You can see these 3 horizons here. And now I'm going to run the faults on this volume. And so here's my fault volume. So all right, click of a button, the user didn't have to do anything. I got my AI faults ready to go. Now combining everything that we showed before, now we have a full comprehensive. Here we had our zones of shallow hazards that we want to dodge. Now we have our gas sand reservoir that we want to try to isolate using our lithophase prediction. And now, like I said, you have this full comprehensive 3D model that includes not just the shallow hazards that we showed, but now we also have the gas sand reservoir, the shaly gas sand, the wet sands, and now we have the greater faults in there. So this is going to help the geoscientists decide where they actually want to drill. And if you combine all of this information into a single self-organizing map, you have this entire model that can represent your entire basin, right? So here you can see we have all of our different neurons, all of our different fault neurons. You can identify which of these are your lithophases. So like I said, now you have this full comprehensive model that's going to compartmentalize your reservoir for you and help you decide where you actually want to go ahead and drill. Those are the attributes. That was a lot of material.